Okay, today we will be discussing lines and planes in space. Today specifically we'll discuss lines in space, as well as planes in space, and then tomorrow we will discuss distance in space. So if I accidentally gave you any distance problems on today's assignment, just save those for tomorrow. So when we discussed lines in a two-dimensional coordinate plane, we graphed them by finding the y-intercept, finding the slope. When we're in 3 space, slope is a little bit more complicated. So instead of finding what we think of as slope in two dimensions, we're going to go ahead and use a direction vector to help us graph our line. To determine an equation passing through a point and in the direction of a particular vector, okay, we're going to use our knowledge that parallel vectors are scalar multiples. I think we looked at that last week towards the beginning of the week in our homework. So if we have a point P and Q on a line, then when we create the vector PQ, it should be a scalar multiple of v. Whether the scalar is positive or negative, it doesn't matter because they'd both be parallel. So when we write the vector PQ, okay, it's going to be a scalar multiple of the direction. Okay, we can also use the fact that we are finding our vector by taking the terminal point minus the initial point. That's what you see highlighted right here. Okay. And then this last vector is just that scalar multiple multiplied through. We are actually going to use our knowledge of parametric equations to help us write the equation of a line. First of all, on our previous slide, we wrote our vectors in 2 different ways. You see right here, I have basically set each component equal to each other. As far as the left side of each of those equations is the terminal minus the initial point, and the right side of each of those equations is the scalar multiple times the vector. Second line, we just see the equation rearranged. This is how you're going to see it most times. X equals Y equals Z equals. These are called the parametric equations of the line. We also have what we call the symmetric equations of the line, which basically means you're solving for t in the equations above our in our parametric equations. Okay, that t is going to be the same throughout, and it's going to be written with that t value. The x and the t will stay. The x naught, y naught, z naught, the a, b, c, those will actually be numbers. So we can solve for t in each of those equations, and we can write what's called our symmetric equations of the line. You will be expected to be able to write both for any line that I give you in the 3-dimensional space. Okay, so here's a little summarization of basically the past 3 slides put together. Okay, we have a point P, and we have our parallel vector V. Okay, taking those, we can write our parametric equations as such. Okay, x, y, and z will stay, t will stay, x naught and y naught, z naught, a, b, c, those will be the numbers that you get from your point and your direction vector. Now, as long as all three components of the direction vector are non-zero, you will be able to write the symmetric equations as so. If there is a non-zero component, you won't be able to write all three symmetric equations. Okay, so here we have an example where we have a line that has the point 2, 3, negative 4, and we want to be parallel to the vector negative 1, 2, 5. So this is giving us a point on the line and the direction of the line. So to write our parametric equations, okay, we have our x equals x naught minus at, or plus at, excuse me. So we're going to take the 2 from our point. Our vector component is negative 1 for x, and so we have 2 minus t. And then for y, we'll take 3 is from the point, and then that 2 is coming from the direction vector. And then for z, negative 4 is coming from the point, and then 5 from the direction vector. In order to write the symmetric equations, all we're going to do is solve for t. And so these are represented here. This is representing what t equals. You could write this first one as 2 minus x over a positive 1, but I would prefer you to leave it as the x minus 2 over negative 1, since negative 1 corresponds with our vector. I'd like you to keep it the same number. So if you have a negative value for any of your vector components, when you're writing the symmetric equations, keep them as those negative numbers in the denominator. Okay, here's an example where we are given 2 points on a plane, or on a line, excuse me. And so here are our 2 points. Now, we know how to write the equation of a line given a point and a direction. However, if we have 2 points on a line, then we are able to find the direction by finding the component form of the vector between those 2 points. So our direction vector we find by just taking one of the points minus the other. It does not matter which one you take first. One isn't necessarily the initial point. Whatever vector you get, if you were to do the opposite way, it would be parallel still. So it's not going to affect your answer in a negative way. Your answer may just look a little bit different than the person sitting next to you if you guys use a different initial point from each other. Basically, it'll just be opposite. So first you find the direction vector. So our direction vector is 2, negative 4, 7. Okay, now that we have that, we can write our parametric equations. Okay, just like when you write lines in 2 dimensions, okay, if you have 2 points, it does not matter which point you pick after you find slope. Same goes here. We can either pick the first point or the second point, but here again, our equations are just going to look slightly different from your neighbor if you pick different points. So here, I just picked the first point. The numbers are easier to work with. And so my parametric equations, x equals 1 plus 2t, y equals 2 minus 4t, and z equals negative 2 plus 7t. You could have picked the second point, and you would have had x equals 3 plus 2t, y equals negative 2 minus 4t, and z equals 5 plus 7t. And then your symmetric equations, just solve for t with whatever parametric equations. And so all of those numbers should correspond to your parametric equations. When you're doing this, please do not switch the point you're using from your parametric equations to your symmetric equations. I'd like you to be consistent from one to the next. Okay. Now, since we could have multiple answers, you can check your answers quickly. Okay, you can plug t equals 0 into your parametric equations and make sure that they give you, well, you'll see that you get the point 1, 2, negative 2. You also see if we plug t equals 1 into our equations, we get the point 3, negative 2, 5. These equations are not unique, and so there could be multiple answers, just like when we are in a two-dimensional plane. Okay, we can describe the same line in numerous ways by just making them scalar multiples of each other. Instead, here we can just pick different points in that same direction and make our lines, our equations look a little bit different. Okay, so now we're going to look at planes in space. We've looked at lines. Now let's step it up, and we're going to look at planes. You worked with the intersection of planes back in Algebra 2 and in pre-calculus. We've talked briefly about a plane. We know that our 8 octants are broken up by the xy plane, the zy plane, and the xz plane. Now we're going to look at equations for planes. So in this picture, we have a point P, x naught, y naught, z naught, and then we have a vector n. The vector n is normal to the plane, which is highlighted in pink. Now, for any point Q that actually lies in the plane, the vector PQ will also be in the plane. This will be important as we get into actually writing the equations, and it will be important when we come back to this normal vector n. Okay, so if vector PQ is in the plane and vector n is perpendicular, or what we call orthogonal when we're talking about vectors, we know that their dot product has to be 0. So we know n dot PQ is 0, which means n, our vector ABC, when we take the dot product with PQ, x minus x naught, y minus y naught, z minus z naught has to equal 0. So when we actually take the dot product, we get this equation right here. So what I just highlighted, this is the equation of the pink plane. We can find the equation of a plane from a point in the plane and the normal vector to the plane. Okay, so here's your standard equation of the plane containing a point and the normal vector. Okay, so this is what you're going to typically write. Now we can distribute these terms. You know, when you take a times negative x naught, b times negative y naught, and c times negative z naught, you're going to get 3 constant terms, which can be added together, and you could write the general form as so. So when I ask for the standard equation, okay, you can leave it as a times the quantity, b times the quantity, c times the quantity. If I ask for the general form, that means I want you to go ahead and multiply it out and combine those constants together. But notice how both of them are still set equal to 0. So here's an example. We are given the normal vector 3, 1, negative 2 to our plane containing the point 2, 3, negative 1. So to write this in standard form, Okay, our a, b, c is going to come from our vector. So you see our 3, 1, and -2. And then we'll multiply those by the quantity of x, y, and z minus whatever corresponds in our point. So we have 3 times the quantity x minus 2 plus 1 times the quantity y minus 3. And then minus 2 times the quantity x minus -1, or excuse me, z minus -1, so we write it as z plus 1. Now if we want the general form, then we can go ahead and distribute those through, and we can combine our constants to this -11 right here. So our standard form is here, and our general form is here. Our next example is writing an equation of a plane given 3 points. So in this example, we have the points 1, 2, -1, 4, 0, 3, and 2, -1, 5. Those 3 points lie in our plane, and we want the equation of the plane in general form. So first of all, we know how to write the equation of a plane given the normal vector and a vector that lies in the plane. So what we need to do is we need to find a vector orthogonal to our plane, which means we need a couple vectors in our plane so that we can do the cross product. So what I've done here is I've taken the first and second point, and I have found the vector that's formed between them. So I have the vector 3, -2, 4. And then I took the first and the third point here, and I found the vector between them to get me the vector 1, -3, 6. So those are two vectors that lie in my plane. So when I take their cross product, the result will be a vector that is orthogonal to those two vectors, or in this case, orthogonal to the plane itself. So here's my cross product. We put in I, j, and k. Then we put in our two vectors, and we end up getting the vector -14, -7. So now here is the vector that is orthogonal, and we can use any point to write the plane. And so this, when I write the equation of the plane down here, I went ahead and used the first point. Since there is no x component to the vector that is orthogonal, our x's disappear. And so we have -14 times the quantity y minus 2 and -7 times the quantity z plus 1. So once we distribute, we get this right here. I am fine with you leaving it like that. You can also reduce by dividing by -7. Either way works for me, but I am okay with you leaving it the first way. Okay, I am going to now show you a couple different ways to graph planes in our 3D space. So the first way we can do this is to actually find the intercepts for each axis or each plane. So we're going to start out with this equation right here. And what we can do is the first thing I would do is I would go ahead and set it. I would move the constant over to the other side. So x plus 3y plus 4z equals 12. And then what we can do is we can look at intercepts. So what happens when both y and z are 0? Then we're looking at where we are on the x-axis. So if we put a 0 in for y and a 0 in for z, then we have x is 12. So 12, 0, 0 is 1 point that lies in our plane. Then if we say, okay, x is 0 and z is 0, then 3y equals 12, so y is 4. So the point 0, 4, 0 lies on our plane. And then we can do the same thing for z, saying, all right, x is 0, y is 0, so we have 4z equals 12. Our z-intercept is 3, so we have the point 0, 0, 3. We can then plot these 3 points and connect them, which I'll show here on the next slide for you. Okay, so here I plotted the points 12, 0, 0, 0, 4, 0, and 0, 0, 3, and I just connected them to make a triangle. Now, obviously, this plane goes on forever in all directions, but it's a little hard. You can't really graph that. And so what we've drawn, each of these lines is called a trace. So that way we can kind of get a visualization about what angle through our 3 space this plane is cutting through. Another way we can graph these planes is to actually find the traces themselves. So for example, to start off, this is the same plane. Here, if we let z equal 0, we get the line x plus 3y equals 12. So we can use our knowledge of graphing lines in a two-dimensional plane to graph the line x plus 3y equals 12. Okay, so we know that the x-intercept's 12, the y-intercept's 4, and we can connect those two. So in the same fashion, we can plug 0 in for x, as well as 0 in for y to get the other 2 traces. So then we can graph the line 3y plus 4z equals 12 in the yz plane, and then x plus 4z equals 12 in the xz plane, and here we have our 3 traces that make up our plane. Okay, so here's another example. We have 2x minus 4y plus 4z minus 12 equals 0. So if we plug 0 in for y and z, we get the coordinate 6, 0, 0, which we plot right here. If we plug in 0 for x and z, we get the point 0, negative 3, 0, which we plot over here on the negative side of the y-axis. And then if we plug in 0 for x and y, we get the point 0, 0, 3, which we can put right here. In my opinion, finding the points on the axes is an easier way to graph these than actually finding the traces, but you can choose whichever method works best for you. Okay, not all planes are going to have an x, y, and z intercepts because sometimes we could have a missing variable or missing variables. In this case, we have 2x plus 3y minus 6 equals 0. Anytime we have one variable missing, our plane is going to be parallel to the axis of the missing variable. Okay, so keep in mind an axis is a line and we're talking about a plane. So the plane is parallel to the axis of the missing variable. So in this case, we have 2x plus 3y minus 6 equals 0. We are missing a z, so this particular plane is parallel to the z-axis. Okay, so when we find our traces, okay, this is going to be the best way to do this. The xy trace is this line. Okay, putting 0 in for z is going to give us this line. The yz trace is y equals 2, and the xz trace is x equals 3. Okay, so those combined, we have this plane here in red. Okay, and I did add this extra line up here just to make it look like a plane. Okay, what I'm highlighting here was our 2x plus 3y equals 6. Y equals 2 would be this line right here, and x equals 3 would be this line right here. And just to make it complete, I made it a rectangle so we can visualize that plane. Okay, now my second example on this page, we're going to talk about a plane who's missing two variables. Now in that case, the plane is actually going to be parallel to the coordinate plane of the missing variables. So in this equation, we have 2x minus 6 equals 0, or x equals 3. Okay, so you see my picture, I have this blue, I just drew a square, rectangle, whatever you want to draw, through x equals 3. Since x is the only variable present, this is going to be parallel to the yz plane since there is no y or z variables in the equation. The last topic we will talk about today is the fact that any two planes that are not parallel or identical, they will intersect. Okay, and when they intersect, they are going to form a line. So what we are going to work on is actually finding the equation of the line where our two planes are intersecting. So basically, our strategy for finding the line of intersection for two planes is to take our two equations and eliminate a variable so that we can write two variables in terms of the third. So in this case, we have x plus 3y plus 4z equals 0 and x minus 3y plus 2z equals 0. So what we're going to do is we're going to choose a variable to eliminate. The easiest one, well, I mean, you could do any of them. Y's would probably be a good choice. In this case, I went ahead and chose x's to eliminate. So to eliminate x, I multiplied the first one by -1. So when I added the two new equations together, x was eliminated and I was left with -6y minus 2z equals 0. Okay, so our goal is we're writing one variable in terms of a second. So in this case, I went ahead and I solved for y, and so y is -1/3 z. So what we're going to do is we're going to take that and we're going to substitute that into y for one of our equations. So I chose the first equation. I went ahead and I plugged this -1/3 z in for y, combined like terms, and I solved for x, so now I have x in terms of z as well. So you see I have two variables who are in terms of the third variable. What we can do now is whatever variable you have in common with these two, so y is in terms of z and x is in terms of z, I'm going to say that, well, z is going to be my t, which means I have, instead of x equals -3z, x equals -3t. Instead of y equals -1/3 z, I have y equals -1/3 t, and z equals t. So now I have parametric equations for the line that is the intersection of my two planes. This is actually the end of notes today. Whatever time you have left, you can work on your homework, which I have written on the board for you. I will post this on my website, so if you need to go watch it again, you are more than welcome to do that. It will be on my website with the link to the YouTube video just right there. So have a good Monday, and we will see you tomorrow.
Made with Doodlecast Pro.